Good morning, students. Today we are going to discuss on Legendre polynomial from Legendre differential equation. And this is your Legendre differential equation. The solution of Legendre differential equation is nothing but Legendre polynomial. And of course, we know that this is 300 years old subject. So around 17th century, it was introduced by Legendre. So Legendre differential equation. But mainly this is used in quantum mechanics. Over 100 years, the scientists, they belong to quantum mechanics. They are using mainly Legendre differential equation. All because of the solution of the wave function in a hydrogen atom. Suppose when you are going to consider a hydrogen atom as a spherical symmetric one, then the solution of a hydrogen atom, that which is nothing but the wave function. And we will be using only the Legendre differential equation. So we can get the solution of hydrogen atom as a wave function, which is nothing but Legendre polynomial. And in fact, n is here in the differential equation, but here it is considered as n is a constant. Whereas in hydrogen atom, the differential equation where n is the principal quantum number. So when n equals 1, which we say as a ground state wave function. When n equals 2, we say this as first excited state, second excited state, and goes on. Okay, so with this introduction, we will start Legendre polynomial. So Legendre polynomial is a solution of the Legendre differential equation, and it is given by this. So wherever you find the differential equation of this form, immediately you can consider that this is your Legendre differential equation. And of course, we are going to have the power series, and in the last video lecture, we introduced this power series, which is we are going to assume the solution as y equals sigma over r equals 0 to infinity ar x to the power minus kr, provided a naught is not equal to 0. The first constant should not be equal to 0. So that's why it is termed as a naught is not equal to 0. So this is your solution. Now just differentiate that solution, because the differential equation contains second order differential equation and first order differential equation. So we have to differentiate once and two times. Only then we can substitute in the differential equation. So differentiating this, you will get equation 3. So dy by dx, differentiate with respect to x. So you will have ar x to the power k minus r, that will give you k minus r x to the power k minus r minus 1. Differentiating again with respect to x will give you this equation 4. So ar k minus r, let it be like this. You have k minus r minus 1 x to the power k minus r minus 2. Now use this equation and this equation and this equation, 3 equations in Legendre differential equations, So we will have this term, correct? So you have 1 minus x squared d squared y by dx squared minus 2x dy by dx plus n into n plus 1 y, which is equal to 0. Is it okay? Very simple. Now we can simplify 1 multiplied by this minus x squared multiplied by this. Similarly, 2x multiplied by this. When you are going to multiply 2x, you know x to the power minus 1 is there. So that one will get cancelled. As usual, in the last video lecture, we did the same procedure. Similarly, x squared multiplied by this, that will cancel with x to the power minus 2. Okay. So I have pulled ar out. This is your first term. Okay. This is your first term. 1 multiplied by, and this is your second term, correct? You have, see here, you have 1 multiplied by this term minus x squared multiplied by this term will give you x to the power minus 2, and x squared will get cancelled. See here, there is no x term here. Out of this third term will be your 2x multiplied by this term. See, you have this term. This will be your last term. Okay. Now I have written the same term here. Now look at the second term and third term, fourth term, which contain x to the power minus kr as common. I can pull it out. Here x to the power minus kr, here also you have x to the power minus kr, here also you have x to the power minus kr. So I can pull it out. And I can write this as n into n plus 1, and this term minus k minus r, and this term will be minus 2k minus r. Is it okay? I have pulled common terms out from second term, third term and fourth term, and I have written as second term in the next equation. Is it okay? Now K minus R and K minus R, I can take it out, say as common. One thing, K minus R and K minus R, I can take it out. So out of these two terms, I can pull K minus R out. So I have written K minus R out. Remaining term will be K minus R minus 1. Here it is, already one minus is here. So this will become plus. So plus 2. Minus 1 plus 2 will be minus 1 plus 2. Will be plus 1. So in the last term, we have simplified the last term as exactly like this. Is it okay? Now K minus R, as I said, K minus R I have already taken out. So this becomes K minus R plus 1. Okay, in the last term. And this term can be written as n square plus n square plus n. And here I can write this as K minus R multiplied by K minus R. So K minus R whole square. K minus R multiplied by 1. So that will give me minus K minus R. Is it okay? So this can be replaced with this term in the next equation. So we have written the next term. N squared minus K minus R whole square, n minus K minus R. Is it okay? Now we know that A squared minus B squared formula, which is nothing but your A plus B, A minus B, I have written like this. Second term as it is like this. And pull common terms out. Pull common terms out. So that will give me n minus K plus R. See, n minus K plus R as common, and remaining term will be n plus K minus R. Here it is plus 1, so plus 1. See, here we have common terms. This is a common term. I can pull it out. This term I have written like this. Here it is plus 1, so I have written plus 1. And of course x to the power K minus R, your AR. Now this is the final equation. So we have simplified as much as we can. So we have done. Now as usual we can do for R equal to 0, R equal to 1, x to the power K minus R, what we have seen earlier in the last video lecture. So we are going to follow the same procedure. Okay. Now equating the coefficient of highest power. First we will go for x to the power K. X to the power K implies that R equals 0. If R equals 0, suppose R equal to 0, we can't go with this. So there is no coefficient of x to the power K. So it will be 0. Coefficient of x to the power K is 0 here. Here x to the power K is remaining expressions. So we have now A naught, R equal to 0. So A naught. Okay, R equal to 0. So n minus K, and n plus K plus 1. See, n plus K plus 1, which is equal to 0. As we discussed earlier, A naught should not be equal to 0. The first constant should not be equal to 0. So A naught will not be equal to 0. What about remaining term? N minus K equals 0 implies that n equals K. Like in the last Hermite differential equation, we did the same thing. So K equals Nk. K equals N, or N equals K. The next one will be N plus K plus 1 equals 0 implies that K equals minus N plus 1. Okay, so this is your first case and this is your second case. So we are going to use to find out the Legendre polynomial of the first kind using this one and second kind using this one. And we are going to add these two to get the complete Legendre polynomial. So that's the idea. Is it okay? Now equating the coefficient of x to the power K minus 1 to 0 now by putting R equals 1 now. So in the same expression we are going to have R equals 1. So x to the power K minus 1. Okay, so that will give me, so this is the original equation 5. So now when R equals 1, that will give you x to the power K minus 1. And there is no coefficient of x to the power K minus 1. As usual, this will become 0. You will have A1, n minus K plus 1, n plus K. R equals 1, this one and this one will get cancelled. You have n plus K equals 0. Okay, so it implies that A1 equal to 0. The second constant A1 equals 0. Now of course remaining that we can write this as n minus K plus 1 equals 0. So K equals n. So n minus n plus 1, this one will cancel, 1 cannot be equal to 0. So only possibility is A1 should be equal to 0. Okay, 1. Now again the same thing that we know already, if A1 equals 0, A3 will be equal to 0, A5 will be 0, A7 will be 0. So all odd numbers will be 0. So this is the conclusion that we can have from this equation 8, A1 equals 0. Now we are going to equate the coefficient x to the power K minus R. Now look at this equation. We are going to have the coefficient x to the power minus x to the power k minus r, and of course the coefficient of x to the power k minus r from the second expression is given by this. So we know. What of this one? When I write, I need to have x to the power k minus r. So I will have to write here r as r plus 2. That 2, these 2 will get cancelled. You have k minus r. Is it okay? See here, we need to have the coefficient x to the power k minus r. Here already we have k minus r, x to the power k minus r. We need to have x to the power k minus r. By putting r equals r plus 2, that 2 and minus 2 will get cancelled. So you will have x to the power k minus r. So this becomes r plus 2. Okay, r becomes r plus 2. Plus 2 minus 1 will give you plus 1. And what of this term? Here r equals r plus 2. So it has to start 2 terms earlier. So this was discussed in the last class. So we have r equals 0 will become r to the a r minus 2. Is it okay? So now we have compared the coefficient of x to the power k minus r. Okay. So from here I can take this term to that side and I can find out ar equals. Take this term to that side, right hand side, and you will get ar equals this expression. This expression multiplied by ar minus 2. Now use the first one, k equals n. K is 1, n equals k. So your ar equals, instead of k you substitute n. So n minus r plus 2, instead of k, n minus r plus 1 divided by, you will have n, here it is k equals n here. Okay, k equals n means this one will cancel, you have r. And k equals n means you will have 2n minus r plus 1, 2n minus r plus 1. So ar minus 2. So now from this we can get all even numbers. For example, when you substitute r equals 2 here, so r equals 2, that will give you a naught. R equals 2 will give you minus n, r equals 2 will give you n minus 1. So your a2, the expression for a2 is given by this expression, equation 11. Now putting r equal to 3 here, so you will get a3 which is equal to a1. So here it is a1. So r equal to 3, here also you can write r equal to 3, substitute r equals 3 will give you this. See, as I said earlier, you have found that a1 equals 0, so your a3 will be 0. Similarly you can go for a5, a7 and all those things will be 0. Now we will go for next term in even numbers, r equals 4. When r equals 4, you will have a4 which is equal to n minus 4 plus 2, n minus 4 plus 1 divided by 4, 2n minus 4 plus 1, r equals 4 means this becomes a2. So a2, you will get this expression. We know that a2 is given by this. So you substitute for a2 here, you will get in terms of a0. So every even number that will be in terms of a0. So that's the idea. So a4 is given by this. See here, you have n minus and minus will get cancelled. You have n minus 1, n minus 2, n minus 3 divided by 4 2s are 8. So you have 8 here, 2n minus 1, here 2n minus 3 times a0. Any doubt? a4. Now we know that the solution which you have assumed in power series, y is given by this. And of course we know that all odd numbers are equal to 0. So you can expand this in terms of expansion. a0 x to the power n, putting r equal to 0, r equal to 1, 2, you will have all those things. Now all the odd numbers will become 0. Take the even numbers alone. a0 x to the power n, a2 x to the power n minus 2 goes on. Now you just pull a0 out because a2 is in terms of a0, a4 is in terms of a0. So you can pull a0 out. So a0. Remaining term will be xn. What is the expression for a2 which you have found already? a2. You substitute here. So multiplied by x to the power n minus 2. This is your a4, expression for a4. So which is given by this x to the power n minus 4. Now you substitute a0 is given by this. If you substitute a0 is given by this, you substitute here and get the expression, total expression for your first Legendre polynomial. So this is your first Legendre polynomial, first kind. So the above equation, the above solution is known as Legendre polynomial or Legendre function of degree of n of first kind. So this is case 1. Okay. Now we have to go with the case 2, which is k equals minus n minus 1. Can you remember this one? K equals minus n minus 1, case 2. So your AR is given by this, and you have to substitute for k as minus n minus 1 here. So you will have AR which is equal to, instead of k you substitute minus n minus 1. So already minus r is there, so plus 2. Now k minus r, again minus 1 minus 1 minus r plus 1 divided by, instead of k you substitute minus n minus 1, instead of k you substitute minus n minus 1. Okay, you will have this expression AR minus 2. We can simplify now. So minus 1 plus 2 will give you plus 1. Minus 1 minus plus 1 will cancel, you have minus n minus r divided by, this one will be your 2n. So 2n plus r plus 1. n will get cancelled. Minus 1, that one also will get cancelled, you have minus r. Is it okay? Simple. Now I can pull minus minus, I can pull minus, and this minus will get cancelled. Okay, I can pull this minus sign out and minus r will get cancelled. You have plus r, n plus r. Now remaining this term, minus n, that will give you plus n, minus r will give you plus r, minus 1 plus 1 will give you minus 1 divided by rest of the term. So your AR is given by complete expression for Legendre polynomial, that we can get it. Okay, any doubt in terms of AR? Now as usual, so this is your AR expression for your AR, and putting r equals 2 here. So you have to substitute r equal to 2. So r equal to 2 means n plus 2. Here it is n plus 1 divided by 2n. R equal to 2 means 2 plus 1, which is equal to 3. So r equal to means you will get a0. So a2 is in terms of a0. Now r equal to 4. So r equal to 4, you substitute r equal to 4 here. So a4 equals n plus 4, n plus 3 divided by 4 times 2n plus 5, a2. You substitute the expression for a2 here, that will be in terms of a0 for a4. So your a4 is given by this expression in terms of a0. So you substitute a2 is here. You substitute for a2 and get the total expression a4 is given by this. Any doubt? So we have found out now a4. So as usual, you substitute for a0 equal to this one, then you have to substitute in this expression. See here, in this expression. So to have a complete series, so you have a0 x to the power n plus a2 x to the power n minus 2 plus a4. We have found out for a0, a2, a4 for the second kind. For the second kind, you will have this term. So this term multiplied by, so this is your first term, this is your second term. Okay, this is your first term and this will be your second term. So this is how Legendre polynomial of second kind. Okay, so now the above polynomial is known as Legendre polynomial q of x. Earlier it was as Pn of x. So for the first kind, so Qn of x of degree of n of second kind. Adding the case 1 and 2, case 1 and case 2, we can get the complete Legendre polynomial. The first and second kind order, we have the total Legendre polynomial is given by y equals c1 times p1 of x plus c2 qn of x. Okay, so this is your complete solution of Legendre polynomial from Legendre differential equation. So this is for the first kind and this is for the second kind. You have to add to get the total Legendre polynomial. Okay, that's all.